is Griffiths E&M section 5.1.3 currents part 2. In the last video we described how a line current was defined by some line density times the velocity at which that line density is moving. Okay. Just like in electrostatics where we had different types of charge distributions, we had line, surface, and volume charge densities. We have something similar in currents. Okay, so if I have so this is an example of current moving along a straight line, and if I have a surface that carries a current, I can go ahead and look at some sliver, some ribbon of that current. All right. And if I needed to find what the total current was, I would take that ribbon and I would look at other similar ribbons next to it. Right. And each of these ribbons has some thickness, dl, perpendicular. So some dl is denoting the fact that it is some infinitesimal length wide, and the perpendicular refers to the fact that you're defining that drawing so that each of these lines are perpendicular to the edge. I can go ahead and define a surface current density, K, which is related to change in the current that flows through each of those ribbons per unit width. Okay, so this is a current per unit width. All right, surface currents, they exist. And just like how we wrote our magnetic force in some generic form, V cross B dq, this dq can be written as the product of our surface charge density times an area just like we did in electrostatics. But now this thing right here, the product of those two is the surface current density. All right, we can also have a volume current density. So let's say we have some cylinder, and instead of looking at little ribbons inside of there, I will look at some rectangular chunk or cross section through. That rectangular cross section has a area at the surface, dA, perpendicular, right? That is some infinitesimal area that lives on the surface of our volume, and it enters into that volume perpendicularly. So this is, instead of being the current that flows per unit width, this is the current that flows per unit volume. Or rather, sorry, per unit area. That is a volume current density J, which is the amount of current that goes through that piece normalized by that And just like the surface current being defined as the surface charge density times an area, that was, that's not quite right. That's times V. The volume is our volume charge density times a velocity. All right, and then you can do the same kind of expression where you can calculate the magnetic force using the volume current density. Great, let's do an example. Example 5.4 says that I have current I current I flowing through a cylinder where I have some volume current density J, which is some constant K. Unfortunately, constant K looks like surface current density, but it's not that in this case. I'll go ahead and say that this is the magnitude K times S, where S is the distance from the center of my cylinder. Okay. The direction is along the cylinder. Okay. So what is the total current going through that cylinder? I had that long pause because I was looking at my notes, which I was trying to, which were for part B, and that didn't match really what example 5.4a was. Okay, so my goal here is to calculate using this volume current density the total current that's traveling through this cylinder. Okay. So if I were to try to sketch what this volume current density looks like, when I'm at the center of my cylinder along this dashed line, S is 0. So I have really no current, okay, traveling there. But as I travel farther and farther away from that center, the current gets bigger. Okay. So let's calculate what that total current is. It's tempting just to take the product of the volume current density and an area, but because that current changes in space, we have to go and take the integral. So I'm going to take the dot product of the current density and the area that is perpendicular to that surface. Okay. I'll call this the z hat direction. So then I can go ahead and write, I won't write that there. This is integral of ks in the z hat dotted with some infinitesimal area element in cylindrical coordinates. And if you build that correctly, that will be ds s d phi. Okay, and I will say that is also in the z hat direction. Okay. Usually these point outside of the object, but you can imagine doing the same for here. Okay. So this is integral of k s squared ds d phi. I need to go ahead and integrate from 0 to 2 pi, 0 to, I guess I should say what the size of the wire is, radius a, so 0 to a. I'm going to get 2 pi 1/3 a cubed times k. That's the total current that travels through that wire.